Okay, so this is gonna be our intro to MATLAB class. As far as what we're gonna cover, there should be. How do I do this thing? Darn it. Okay, here. Okay. As far as what we're gonna cover, page down. Okay. So first, what is MATLAB? It's essentially one of the probably a half a dozen or so different software systems that allow you to do scientific computations. It's relatively high level, so you don't have to deal with the details of how the computers are working and how to deal with the nitty-gritty details of programming. So development can be pretty rapid. The graphical user interface, the way you interact with the system is pretty nice and well worked out. So it's one of the nicest things that I've seen. It's comparable to other systems, to Spider when you're dealing with Python or to Jupyter. But it's another one. It's probably best in terms of features it offers. MATLAB is optimized for doing numerical computations, and even though you're writing scripts, snippets of code that are interpreted when they're run, the operations are actually optimized, and if you know how to use it, the computations can be pretty rapid, even on large data sets. So this is one of the advantages. Another one is that MATLAB deals with a lot of graphics. It can make plots in just XY plots and three-dimensional plots. So those things are pretty strong on the MATLAB side. And MATLAB is huge. There's a lot of libraries dealing with different problems spanning many different parts or domains of science and engineering. We're gonna go only through very top, very basic operations, just to let you use the system without going into details of one specific package or another. So this is essentially intro to MATLAB, to graphical user interface and just basics of what can you do with it. The plan for the 3 days is to cover the user interface and basic operations, basic math that you can do with in MATLAB, plus things like reading and writing data into files and trying to see how you can debug or check what your program is doing. Tomorrow we'll continue going into more details and more complex operations. Plus, we'll cover generating XY plots, two-dimensional plots. What's gonna happen on day 3 is still open, depending how we fare, what we're gonna be able to cover over first 2 days. We will see what's gonna go into day 3. If you do have any particular requests about what to cover on day 3, let me know tomorrow, and then I'll try to accommodate if it makes sense. I wouldn't like to go into too much details of one particular packager, because it's not the point. The point is to get you going with MATLAB so that you can play with this thing on your own. So that's the plan. It would help if you have MATLAB installed on your laptops or your computers, whatever computer you're using. I mean, this way you'll be able to type in or follow whatever I'm doing with in MATLAB on my side, and then if you run into any problems, you should be able to share the screen and then you enable this thing and you'll be able to show me if things are working or what's not working. We can try to fix the problems. Okay, and that's about it. I mean, the PowerPoint presentation does have a few pages, which the intention is to make it more like a reference guide. So I'm gonna quit PowerPoint now. You can check what's in the slides offline, but let's switch to MATLAB. Okay, I've got it running here. If I quit it, okay. If you installed it, hopefully you did manage to install. If you got problems with installations, then please let me know. Okay, and then I'll try to accommodate. Okay, and help. Okay, so let's start it. When you start it, it's gonna take a while. It's once more, it's a large program, and it takes a while to open the user interface. But once it opens, well, let's hope it opens. Cool. Hope it starts. Okay, here it goes. Once more, it's a large thing. So, okay, so when we start it up, we're gonna see a big window with a bunch of sections. Okay, on the top there are tabs that let you switch between different panels and different options that you see. Most often you're gonna end up in the editor tab. This is where the programs are either developed or run or debugged. So this is typical setting for the editor. Okay, and depending on the choice, you're gonna see the different options showing up here in a toolbar. But in most of the cases, the lower setup is gonna stay the same. Depending on customization, how this thing is organized, how this thing was set up, you might see different layouts of the windows, but typically you're gonna see somewhere the editor window where you edit your scripts. You're gonna see a command window where you can type commands and interact with and try your computations, interact with the MATLAB in an interactive way. Okay, somewhere there you're gonna have a workspace panel. This is gonna show you the state of the computations, all the variables, whatever is done, whatever results you're gonna see showing up here. And then there's gonna be a current folder shown here in another window, and this is the place where MATLAB, if needed, looks for scripts. And my suggestion is to set it up to some place on your PC that you know where it is. Okay, depending if it's Mac or Windows, you're gonna see different things, but in my case, I just clicked on the folder here, went and made sure that on the desktop I've got the, why do I have two of those things? Go away. Now I've got 2. Oh, that's a problem. Let's get out of here. Okay, I'm done 1. And on the desktop, I just downloaded the files that were on the Google Drive. So that's where I set the current folder pointing to. And then if you're, let's go back. Let me change this thing. Where are we? I should have a desktop here. Okay. And then W2, I go here. Okay, so if you hover over the directory where your scripts are and you see the notification, as you see here, that this folder is not on your MATLAB path, then follow the instructions, double click on the folder, okay, here, and then it's not gonna be grayed out anymore, and MATLAB is gonna know that if you've got scripts that are going to be sitting here. Otherwise, you might see problems with finding scripts in other directories. So just make sure that directory that all the files are kept is selected as a current folder. Okay, so that's the layout of the screen and what we can do with it. Okay, I'm gonna just open an empty file here so we don't have anything here. And let's try to do something interactively. Okay, you can think about MATLAB as a calculator on steroids, essentially. This thing does essentially math. So if you type something like 1 plus 2 plus 3 or whatever you want, and then you press enter, it's gonna tell you that this sum is 6. If you type any expression followed by enter, then it's gonna be evaluated by MATLAB, and you're gonna see it printed out in a command window. You're also gonna start showing it up in the workspace as this ans variable. This is variable. This is a place in the memory where MATLAB is storing the result of this calculation. Okay, so that's what it's here, and then it's gonna show up in the workspace. Now, if you want to have a more permanent place to store the results of some intermediary calculations, what you do is you can specify a variable, you can specify a name, let's say let's call it A, and you can assign something to it. Let's say we can say that A equals, let's say 1 plus 2 plus 3. Okay, and we can press enter. Now we do see it printed out here, but you also see it showing up as another variable in the workspace, and also set to 6. If we want to have another variable, we can say that B is equal to, let's say, 5. Okay, and then we can press enter. Now we've got A variable set to 6 and the B variable set to 5. We can use those variables in a following calculations by saying, let's say that C equals A times B. Okay, so far we are always seeing the output of something printed out. Okay, if you want to just set the value of variable without having it showing up in a command line, you can follow the line of code with semicolon, and then nothing is printed out. Okay, but you do see C still set to something, to the value that we specified here. Okay, if you want to see, if you want to have values of the variables printed out, you can always say in a command window display, and you can display, let's say, C, and we're gonna get the value of C shown up here. The command window is very convenient for testing short things, setting up temporary variables, doing things interactively. But this thing is not keeping track, not leaving any trace of what you did. It's very hard to reproduce what you did in a command window. So in practice, you're gonna use it just for testing things, checking if things work. But most of the MATLAB code is gonna reside in the files in the editor. What you can do, though, in command window, you can save the state of the workspace. You can save the variables that we've got here that got created while playing so far. In a command window, we can always say save, and we can specify we want to do it to, let's say, my state, I think. And let's see what happens. If we do this thing, now, after pressing enter, you see in your current folder, we do have a file called mystate.mat stored, okay? And now we can read it back, and then we can restore the workspace state, okay? To demonstrate that is really happening, we can first clear, oh darn it. We can clear, as you can see, if you click on the round icon, if you double, no, well, you can make workspace bigger, let's say it this way. But if you right click, you can clear the workspace. Okay, choose the clear workspace. Now confirm delete. I'm gonna check it, do not show this prompt again, so that I'm not annoyed with it. And now we've got workspace cleared out. There's nothing. We return to the starting state. But what we can do is we can do load my state. And as you can see, we restored whatever was present in the workspace when we saved. So this way, if there's a need, you can save the values that you generated while running programs to a file and then retrieve it back. This holds for the values for whatever numbers, whatever variables are present at a given moment of time. But there is no trace of what were the operations that led to generating generation of those numbers. So this is the problem where you can't keep track of what was happening. So that's why command window is used for normally for some ad hoc operations, but normally the program is gonna stay in a file that you're editing in, and then it keeps track of whatever was done. Okay, so on the Google Drive, I dropped the file with the bits and snippets of MATLAB code. Okay, and those things are. I'm gonna go through this file and try to demonstrate what can we do with MATLAB. Okay. Now, for those of you who are familiar with Python and Spider, let's say, or with Jupyter, you are able to run snippets of code in those systems, one block of a commands at a time, and see what happens, and then run another one, and then so forth. This is also possible in a MATLAB. The way you do it is you put double quotes as so-called section breaks. Okay, if I want to make another section, so I've got a section break here, I've got another section break here, another section break here, and then we've got highlighted the blocks of, we've got highlighted a section of a code that's corresponding, that follows the section break. Okay. If there's only a single quote, this is a command. This is just a text describing what you intend to do or what the program is doing. This is for human consumption to keep track of what are computations about, and so that's something which you would normally put into longer pieces of code to document what's done. If you want to put a piece of code, let's say if we want to set the variable a to value of 1, we can put it somewhere into our file. I'm gonna clear the workspace here to make it back console, to make things empty, clear. Okay, and then if we want to run the section we are currently in, this is the one highlighted by on the left side, we can go up here and click on the run section, and then only whatever is within this block of code is executed. So here we're gonna just run one line worth of a program which sets a to 1. Okay, we run it here, and a showed up in the workspace. We did set the value of a to 1. Okay, this is equivalent of going to command window and typing exactly the same command as we've got here. So we can say a equals 1, or we can, let's say here, b equals 2, and now we've got value of 2 stored in a variable called b, and we did it from a command window. This is equivalent to putting b equals 2 in the section and then running the section. Okay, what can we put into variables? Oh, if you got any questions, just let's see if you're not muted, hopefully. If you've got, let me see. Okay. Oh, there's more participants. Someone showed up here. Where are we? Oh, there's. Okay. So if you've got any questions, just here. Going on here. Oh, here. That's what I want. Okay, that's better. Got the Zoom going in my way. Okay. Okay, so if you've got any questions, just ask, just unmute and ask me, and then I'll react. Okay, so what can go into variables? What can we store in each variable? Well, so far we had just single number. We had 1 sitting in A and 2 sitting in B, but in general, every variable in MATLAB is an array or a matrix. Okay. This is why it shows up like a grid here, and then if you hover over, it's gonna show you that this is a 1 times 1 double. Double means it's a so-called double precision floating point number, and 1 times 1, this is dimension of the array. It's just 1, but in principle we can put things that are not arrays, but things like a series of numbers. We can make C equal to 1 and 2 and 3. Let's say a series of 3 numbers. To make a list of numbers stored in C will be surrounded by square brackets, and semicolon prevents command window from spitting it out on the screen down in the command window. So if we execute now, you're gonna have information that this is I don't see it, that this is 1 times 3 array, and it's gonna show you the value as a series of 3 numbers. So in general, the variables are array, and they can be either with 1 dimension, so then those are just a list of numbers, or they can be 2-dimensional, so those are matrices. This is the standard matrix in a sense that you know from the math classes, or they can be 3 or more dimensional if needed. We're not gonna go there, but we're gonna stay within 2-dimensional matrices for the purpose of the class. Now, once you've got values stored in your variables, you can perform operations on those. So let's say I will uncomment something here. So we've got the A set to 2, and I add a semicolon so that nothing is printed out. I'll get rid of the command to make it another command, and I'll get rid of the command here. And then we've got a section of code with 3 lines. If we run it, we can run it by clicking on run section, or another option is if you hover here, it's gonna tell you that you can press Control Enter. So this is a shortcut which makes things faster. We can do Control Enter, and now we've got A set to 2, 4, and C is set to A plus B, which is 6. This is not an equation. In most of the programming languages, including MATLAB, a statement that says something like C equals something else on the right side means take stuff from the right side, perform whatever operations are there, and stick results into what's on the left side. So this is what MATLAB is doing. This is what practically every common programming language is gonna do. All this thing means is take stuff on the right, perform whatever operations might be required, and put the results on the left. Formally, it's so-called assignment statement. Now, what are the operations we can do? If we've got just a single number sitting in our variable, or if we explicitly specify value, we can do standard math, right? We can do normal operations that you would expect any type of calculator can do, with the same rules for computation. So if we type 1 plus 2 times 4 plus 2 times whatever, the precedence is gonna be the same as you know from math. This is the 3 is gonna be squared first, then multiplied by 2. Then this thing is gonna be added to 2 times 3 plus 1. So that's conventional math. One thing for those of you who program in different languages, that is that for the exponentiation, you use caret. Some languages use double star in place of caret. So this is something worth to know. Can we take arbitrary value for the exponent? Well, we can always check. If you don't know what to expect, if you don't know if things work, you can always play with it. It's very hard to break MATLAB, so you can always try it. Worst thing is gonna tell you that you're wrong, which is not a problem. So let's say, can we raise 2 to a negative power, let's say to -1? Yes, we can. 2 to power of -1 is 1/2. It's 1/2. So that's what's happening. Can we use fractional exponents? So this would correspond to things like a square root of 2. If we use 1/2 power, is it gonna work? Yes, it does. So that's fine. Can we square root a negative number? Let's say -1 raised to 1/2, power of 1/2. Yes, we can. Amazingly enough, it turns out that the variables that the numerical values MATLAB deals with are complex. So in many calculations, you're dealing only with real numbers, but depending on the problem, you might have complex numbers with real and imaginary parts popping up. Let's say a proverbial square root of -1, and MATLAB does deal with complex numbers. You can perform computations using either real numbers or complex numbers, and you're fine. If a given value is complex, then it's gonna show up as a real part and imaginary part, using I to denote that this is imaginary part of a complex number. So that's sort of nice. And as you can see, you can play with things and check how things work, and it's one of the useful features of that's one thing that's useful about command window. You can always try things and see if things work before you put them into your code. What are the other operations? Well, standard trig functions, so sine, cosine, and tangent and so forth, all those things will be there. For sines, for trig functions, you specify the angles in radians, right? So, and then you often need pi. Pi is predefined. Pi is predefined as a value of a pi variable, and you're gonna get the pi number here. So if you want to get something like a sine, let's say sine of 180 degrees, you would want sine of pi, and sine of pi is 0. Okay, here we're getting something very close to 0. This is demonstration that computations in general performed by computers are not always exact, and sometimes there are random errors. That's what's happening with the sine of 180 degrees. It's 0, but not exactly in the mind of MATLAB. So you might have things like that, but otherwise it works. If we want to have a sine of 2 pi, or let's say cosine of 2 pi, then we do 2 times pi, and we're getting 1, and this happens to be sort of exact. Okay, so that's those are trig functions. You can, exponential function works as well. It does take negative values, does take fractional numbers, so we're fine. Logs also work. You can have either log of, let's say, log of, let's see, log of 1 is always 0. What about log of 2? Okay, well, it's log of 2 is not exactly nothing recognizable, so this is not the base of the log here. This is actually natural log. Okay, if you want to have a log base 2, yeah, as you noticed, if you want to go back and reuse whatever you use in command window, you can go with your cursor up or down, and then a history list with whatever you typed before shows up, so you can reuse something and then modify it. It saves on typing. If we try to do log base 2, we should get 1. Yes, so log of that's how logs work. That's right. If you got the log base something and the log is of the base, then you should get 1. So this is clearly log base 2. And if we want to have log base 10, we can do log n of 10, and this is 1. So that's how the logs work. This is natural log, this is log base 2, this is log 10. So though most of the common math functions are built in, and they behave as they should, and as you expect. It's just a matter of finding what you need. Another function is square root. This is same as raising something to power of 1/2, but there's another version which sqrt, and then if we do -1, we should have once more just I. So its real part is 0. And the imaginary part is just 1i. So if you want to assign a given complex number to a variable, you can use the same form as you see here. You can say that my c is equal to 1 plus 1 times I. Okay, and then if you see what's in the C, we do have the complex number with the real part of 1 and imaginary part of 1 set there. It also implies that I, a variable, has a special meaning. If you type I, you're gonna see that this is actually the square root of -1. It's not a generic variable that you can use. This is something to pay attention to, because because I is very often used as an index into array. It's used in the programming languages of various sorts. In MATLAB, if you modify I, then all the complex computations might be messed up because you changed I to something else, and I think you can assign something like 23 to I, right? And now if you type I is 23, we've lost imaginary unit here, and if you use somewhere else in your code I as imagine, it might mess up. So thing to remember is avoid using I as a variable that you're using. If you're tempted to use double I, it simplifies things and avoids some bugs that you might encounter. Okay, so that's that's roughly, so those are numbers. Apart from storing the numbers, you can store strings, pieces of text in a code. So you can say, as we've got here, that S is a string. To specify a string, you use single quotes and then enclose the text in a bracket. You can also use double quotes. So if we run this snippet of code, everything here are commands. We've got just one assignment here. If you run it with Shift and backspace, no, let's run it. Control Enter. No, what's going on? No, stop. We go. Where are we? No, stop. I messed up something. I started the wrong stuff. Clear. Okay. I did start something that I didn't want to. Okay, once more. Control Enter. Okay, and we've got our string stored in a variable called S. As you can see, you can tell what's the type of the variable by hovering over. This one says that it's 1 times 16 characters. So this is essentially a list of 16 characters sitting there. We'll go into more details of strings, of dealing with strings tomorrow. But for now, it's just to be aware of that. You can store either numbers in the variables or characters or strings, and that you can store either a single number here, like we've got here, which can be either just the real number or a complex number if needed. Get out of here. And if we want to store more than one value, but the list of values or an array, we can always say v equals, say 1, 2, 3, and now we've got a list of three numbers stored in a variable called b. Okay, so that's math. Okay. Any questions so far? Anyone there? No questions. Okay, so now to create matrices, to deal with the lists of things or matrices, you can set those things explicitly. This is what I was doing here. In this particular case, I've created a matrix with 1 row and 3 columns, right? If we want to check what are the dimensions, what's the size of the array, we can always say size and the name of the variable, and it's gonna tell us that there's a 1 row and 4 columns. This is the same as what you see when hovering over a value. That's right, that this is 1 times 3 double. Okay, if we want to, instead of create an array with 3 columns and 1 row, you want to make 3 rows but 1 column in each, we can, instead of space, we can separate the values with the semicolon, and this way, if we now print D, we can either, as I did before, do display D. Okay, or we can just press D, type D and press enter. And now what you see is we've got a matrix with one column and 3 rows. This is different from what we had before. Let's do it this way. Let's try this one. Okay, so this is our D, and I'm gonna call it D columns. Okay, and then the other one, I can call it D rows. Okay, and then this one is gonna be an array. If I hover properly, 1 times 3, and this one is 3 times 1. The cursor is getting on in the way, but we've got 2 different arrangements of the numbers. If you want to have either both rows and column numbers different than one, we can combine the syntax and say something like here, as we've got in here. This is easier to type. Okay, and if we run this snippet of code now, if we see what's in B, this is just 6 values arranged into 1 column with 6 rows, but in C we've got group of 3 numbers, semicolon, another group of 3 numbers. If we see what's in C, now we've got 2 rows, 3 columns each. So this way we can make matrices by hand. Now let's go farther down. We can perform math operations on matrices the same way as the math rules are. So the simplest thing is we can multiply a value of a matrix by a number, by a scalar. This means multiply by 10 every value in an array. We can check if it works for array C. Let's say, let's make and multiply C by 10. If we multiply it, now every number got multiplied by 10. So that's what we expect from a conventional math. We can also do multiply things on the other side. So now we should have 100 times the values. And yes, that's what's happening. So we can do either 10 times array or array times 10. This is working fine. Now, if we've got 2 arrays and we want to put them together, let's say we've got an array with, let's say 1, 2, and 3 sitting in A. Okay, so let's do it explicitly so that we see it here, or let's do it here. Why not? We can always make ourselves another section. To make another section, you do double quotes, and MATLAB's gonna find out that you want to make a section here. I'm gonna put another double quote here. Now I've got a piece of block that piece of code I can work on. I can say then, let's say equals, for example, 1, 2, and 3. Okay, and then I've got the B equal to, let's say, 4, 5, and 6. If I want to concatenate those two arrays together, I can just say that my AB is a cat, this stands for concatenate, and I've got to specify if I want to put those two matrices together as two rows or one row with more columns, okay? If I want to say that I want to concatenate a long row, well, we'll see. We can specify either one and then do A and B, okay? And if we run this snippet of code, we ended up with AB being 3 numbers in one row and 3 numbers in another. So we're concatenating things by putting A as the first row and B as the second row. So that's how it works here. And if we do A, B, but instead of saying, let's see, A, B, C, let's say, instead of saying we say 2, A and B, if we now run this piece of code, now if we check what's in our ABC variable, this is the one here, now we can, we can see it here, we can always say A, B, C to spit it out in the command window. Now, instead of adding A and B or concatenating A and B as 2 rows, you're just going and putting them together one after another to make just a single row. The reason the reason behind using 1 and 2 as the first argument of the cat function is that we're either concatenating along the first or second dimension of an array. And it happens that first dimension of the array is a row and the second is column. So that's how it goes. And it also corresponds to how do you find actual values of a given array. So far, we're always referring to entire matrix as entire array as the one entity. If we want to access one of the elements, let's say if we go back to AB, so we've got an array with 2 columns and with 3 columns and 2 rows. If we want to get to, let's say, the value sitting, let's say, here in the second row and the third column, we would say A, B, we want to have the second row, so we specify the position in the row here as the first element, and then we specify third column as the second one, and this, if we're lucky, should return us 6. So it means that if we refer to a matrix, first index, first number corresponds to your row, and the second one corresponds to the column. So that's how the indices work. So this is the convention used by MATLAB to access the elements of the matrix. And this is why when you're concatenating, you're specifying either 1 if you want to concatenate along the first dimension, or 2 if you want to concatenate along the second dimension. First dimension is a row, second are column. It takes a while to wrap your head about it and then start to do this thing more or less automatically, but I mean it comes with practice essentially. Okay, and then obviously putting together every piece of data by hand, by typing every number manually is tedious. So there's a number of functions that that you can use to actually generate matrices that are so are common. Okay, one common case is a matrix filled in with zeros. Okay, and this is easy. You say zeros and you specify either one number, let's say 4, and let's see what happens. Well, we've got a square matrix with 4 rows and 4 columns, and the value for each of those is set to 0. Okay, so that's what we've got here. If we want to have different dimensions, different size along each different dimensions, that we can specify 2 numbers. We can say zeros, and then how many columns, let's say we want, and how many rows, let's say we want 2 rows and 5 columns. Okay, and here's our matrix with 2 rows and 5 zeros generated by the function here. And if we want ones, then that's another function called ones, and we can do the same thing. Okay, and here's our 4x4 matrix with filled in with ones. If we want the same values different than 1, how can we generate an array filled in with let's say 55 in each position? Anyone's got a guess? Oh, anyone's there? How to generate an array filled in with 55 instead of 1? Hello? Oh, well, if no one's brave enough, well, and switch back and type what works, which is we're gonna generate ones with 4x4 matrix filled with ones, and then we'll multiply it by 55, and this is gonna generate a matrix with all the numbers set, all the values set to 55. So this way you can generate uniformly filled in matrices, either with the same value, whatever it is. You can just use the rules of matrix algebra to fill in numbers with a uniform number. You can have zeros generated by using zeros function. If you want to have an identity matrix, which is the matrix which is square with the ones on diagonal, you can say you want I and then 4, and now we've got a vector, we've got a matrix with the ones along diagonal and then zeros everywhere else. That's how to generate things that are more or less common when preparing or performing your computations. Now, another common case is you might want to have a series of numbers, let's say going from 1 to 10 or 1 to 100 or from 5 to 77 or whatever, to generate the ranges of numbers. you can say that you want to have a range starting from, let's say, 1 to 10, and this is going to generate you a range of numbers. We can test it, and we can assign it to a matrix. Let's say R equals 1 to 10. Okay, and now if we check what's in R, it's a one row with 10 columns, changing from 1 up to 10, and this is what you see here. And if you hover over, you're gonna have a pop-up telling you it's 1 times 10 matrix with the numbers inside. So that's how to generate numbers. If you want to step by different value than 1, you can say that you want to go from 1 going every half up to 10. And this time, what you're going to generate a series of numbers starting from 1, going through 1.5 to 2.5, go using step of 1/2 up to the final value, which is 10. And that's a lot of numbers. So then you see the display is more complicated, because then MATLAB is spitting out just whatever fits in a window, so it's more messy. Large arrays do look horrible in a command window. But if we assign it to a value, let's say R2 is equal something here, and we put semicolon to suppress the garbage. Now you're gonna see R2. It tells you that this is 1 times 19 double, doesn't show the values. So that's sort of less cluttery. If we want to find what's there, we can always say R2, and we're gonna see the printout. Or we can find only a part of the sequence. Let's say you want to find the first 5 columns of R2 matrix. To do this thing, we can say that you want to R2, and we want to start from the position 1 to position 5. This is the similar syntax, similar way of writing ranges as when generating them. And this is going to return us presumably only 5 values corresponding to the first 5 columns here. Okay, now as you notice, the first value is referred to as position 1. This is different from most of the programming languages, where if you refer to lists of arrays, the first position in a list is referred to 0. This is something to remember, something to be aware of when dealing with MATLAB. If you've got any experience in writing programs in Python or C or Java or whatever, that the indexing of the arrays in MATLAB follows the math convention, where the first row is typically 1. It's not the programmer's convention, where first row or first column is referred to 0. This is something which you should be aware of, because sometimes this leads to errors. So this is another difference compared to other languages. Okay, and then to wrap up the generation of numbers and arrays and just making numbers on the fly, there's more functions that more operations that result in generated matrices. Okay, one issue is, let's say we've got a series. Let's say we've got a series of numbers. Let's say S, which is 1 to n. Okay, let's see. So we've got 10 numbers ordered 1, 2, 3, 4, and so forth. What if you want to have also values from 1 to 10, but we want to resort them in a random fashion? Okay, if we want to reshuffle them. To do this thing, we can use a function called random perm, this one here. Okay, and this is gonna, if we uncomment this line and run our snippet of code, where are we? Everyone undefined word random per run, and should work. Oh, I have a typo and I don't remember what this thing is. So if you're not certain, let's try MATLAB random permutation. Random permutation with a typo. Run the perm, that's what it is. And this is demonstration that if you don't know or you're not certain, you can always try Google. In case of MATLAB, it's gonna probably drop you down to pretty extensive help that's available. And you can access it just from a browser, as I did it before, and this is gonna tell you what this particular operation or function does. Or you can also access it from the MATLAB directly if you do rand perm and start typing, then you're gonna have a pop-up showing up trying to help you with and show what are the options. And if you go to more help, you're gonna see in a window the same thing as we've seen before, the online help. This is one of the ways to learn what's available, what are different variants of function calls. A lot of things can be retrieved this way, so you don't have to memorize everything. If you know just something about roughly what you've got to do, you'd be able to figure out by referring to help. So in this particular case, we want not the random, but we want the rand perm n. Okay, this is should be better if I didn't make a typo. I made a typo. Rand perm, and let's do 10. Okay, and if I run this snippet of code, okay, now we don't have an error. Okay, we didn't. Well, if the command line window is cluttered, you can always right click and do clear command window, and then I'll check it out, and we're clear here. And the same thing, if there's a bunch of junk collected here, we can always do clear workspace and clear it. And then let's rerun our snippet of code here. Where's my random thing here? Here, this is my only piece of code in a block here. I can do control, and here's our randomized sequence. Okay. Other options are you can generate different versions of random numbers. That's what's here. Okay, so now we're gonna make a break for a few minutes. And once more, the only way to start working with to know how to work with MATLAB is to play with it. So all the best thing to do is to just try how to generate a matrix filled up in one way or another way, or how to perform operations. And you can either write those things in a file in the editor and then run it as a snippets of code, or try command windows. That's the only way. Okay, so let's make a break for a few minutes. Let's say now it's 2:49, so let's break till 3, and then we'll continue from then on. If there are any questions, ask. Just ask, or either unmute yourself and ask, or check, or try in chat. Okay, so break till 3. Okay. Okay. Yes. Yeah. When you're gonna make the recordings available?
Available?
Yeah, the recordings.
So we asking for.
Yeah.
They can hear me.
Oh, no. Okay.
So the recording will be available on Thursday. Are you missing a class? Are you trying to be here all 3 days? Because all 3 videos will be available on by Thursday.
Okay, this is Stevie Ream who was asking, so I
Alright,
don't
so
know. Okay.
when he hears me, yeah.
Okay.
Yeah, sorry, I just wanted to ask if we could read the recording, because I missed the first 40 minutes, I think, and, okay.
Yes, it'll be available on Thursday, but in this case, in your case, I did notice you jumped in like around an hour in. Send me an email later today. Try to see if I can release one of the videos to you. So you can catch up, okay?
I'm sorry, can you repeat that? I didn't get that.
You'll get the videos. Send me an email and I'll release day 1 video to you by the end of today.
Oh, okay, gotcha. I'm sorry, who's this talking?
Excuse me?
Who do I send it to? Sorry, I didn't know who do I send it to?
I'm the program manager. My name is Eloy Lopez. You can look me up on the QCB website.
Oh, okay, yeah, okay, Lopez, that's right. I got the email notification from you, right?
Yeah, that would be me.
Okay, thank you.
Yeah, just I'm gonna be gone in an hour because I gotta go to a dentist appointment, but just let me know and I'll try to get the video to you by tonight.
Okay, thank you.
Yeah.
Okay.
Hopefully it's not a class.
Okay. Good. Okay. So, and this is person number 4, huh? Okay. So let's keep going. Get rid of the windows that obscuring me. Okay. Okay. So far, oh, just to finish up with how to generate numbers. Okay, we've seen so far that we can specify numbers in a painstaking way by typing explicitly values. We can, once you've got some starting values, we can start to combine them in a different way. Oh, another nice way of sometimes way of generating numbers. Let's say we've created let's make a series of numbers going from 1 to 10. Okay, this is gonna fill up our array with a series of numbers. Okay, let's make it a little bit longer. And let's say, because of whatever reason, we want to move all those numbers by 1 position to the left, so that we want to start with 2, 3, 4, and so forth, and then end up with 1. Okay, well, this can be done by using the circ shift function. It's gonna take our array, okay, and then shift all the values in a list by 1, and then whatever was shifted out is gonna be attached to the very end. So if we do, let's say, a shifted, that is circ shift of a by 1. Okay, if we do this shift, and if we don't make a typo, and if we run this snippet of code here, now what is our AS? What's going on? AS, yeah, I don't want this thing. I can get rid of this one. I can delete not only everything. If I want to remove one of the variables in a workspace, I can right click and then delete whatever I've got here. So here we had A set to a series from 1 to 10, and now AS is this series shifted to the right, 10 got shifted out on the right side, came back at the very beginning. So this also works for two-dimensional arrays. You just have to specify how to shift along the columns and along rows. To demonstrate this thing, we can make ourselves a let's say identity matrix with let's say 4 by 4. Okay. Now, if we check what's in, let's run this thing. Okay, so now if we want to see what's in I, well, we've got identity matrix. Okay. Now, if we want to control shift it, but we want to shift A. Okay. And we don't want comma, and then I'm gonna see the value. Where is it here? Okay, so here we shifted by 1, and let's make it bigger. And clearly we shifted everything down. We went from diagonal ones to ones going below, and then the last one flipped up. So if there's just one number provided for two-dimensional array, the rows are shifted, or we're shifting along rows dimensions. If we want to shift along 2 dimensions, we can specify a list of numbers. So we can specify, let's say 1 and 1, and this is gonna have no effect, because if we shift everything by 1 column position, 1 row position, nothing's happening here. So this is operation that doesn't change anything. To see if it works, we can specify that, let's say, position A11 is set to 0. This is demonstration that we can assign one particular value or modify one particular position within a matrix by assigning a value to it. So we can set A11 to 0. Okay, if we do this now, I wanted to not A, but I wanted to do it with I. Okay, and then if we check what's in I, okay, so now 1 position is set to 0. We've got only 3 ones. So now if we do circular shift using 2 num list with 2 numbers to denote how far to go along rows and how far to go along the columns, if we do this thing now, 0 went from here, it went 1 position down, 1 position to the right. So now it's ended up here, and then other ones are staying where they are. So this is another useful function to modify arrays. And then yet another series of functions generate random numbers. We went through resorting numbers in a list. If you want to randomly resort an array, let's say, okay, so let's say we've got the array, let's say A, and we set it to, let's see, let's make it an array that's filled in with the values from 55 to, let's say, 65. Okay, so this is our A here. And now we want to reshuffle those numbers. Okay, what we can do is we can first generate a random reshuffled list of indices, right? The indices that are used to get to the numbers in A are 1, 2, 3, 4 up to 10. This is generated by saying that we want the range from 1 to 10, from 1 to 10, but this is just the list going from 1 to 10 by incrementing the value by 1. If we resort, if we randomize it, then let's make it, put it into Ri, and to do this thing is we're gonna do as we had before, rand perm of 1 to 10. So now here we're generating a list from 1 to 10, and then we're resorting it in a random fashion. So now our we've got rand perm. We've got to generate just the random list of indices. Okay, so this doesn't work. We can't randomize a list of things, but we can generate a random list of numbers going from 1 to 10, but in a random fashion. Okay, and now this list, this collection of numbers can be used to retrieve the values from our A array. Our A array is here at this moment ordered, but what we can do is we can ask for our array, but we feed it as an argument here the random number of indices. So we're setting our i's here, and then what this thing is gonna do is gonna resort the values in array A by returning as the first value the value corresponding to whatever was the first well, can do for I. So the first value that we've got is the value corresponding to index equal 2. Then second value is the value corresponding to index of 10, then 8, and so forth. So this way we can reshuffle arbitrary array by providing as a argument to here a list of indices that we want to retrieve one by one. If we want to retrieve so this is what we did here, and we can obviously take whatever this thing does and assign it to another variable, let's say a random. Okay, and now AR is whatever we had here resorted by feeding A with the random list of numbers. If we want to retrieve different bits and pieces of our list, we can use as an argument here, instead of our randomized list of indices, we can just specify a range. If we want to get, let's say, elements from 1 to 3, we can specify as an argument just a list of 3 numbers, 1 to 3. This is what 1 colon 2 means. That's right. So this is consistent. Whatever is used here is going to generate the list of values of A according to whatever the indices are here. Here we've got 1, 2, 3 as an index. So then we're getting first 3 elements of A. If we want to get every other one, it should probably work like this. If we want to go and get every other element, this hopefully works. Yes, we're getting every other one. So we're taking first element and then third and then fifth and so forth. So as you can see, to get values from a matrix, we can either specify one discrete value, let's say A3. Okay. We can specify a list of values, which is either provided as a range, okay, or we can make this list by hand. I guess that if we want to have only position 1st, 5th, and 7th, we can just specify as an argument a list of numbers, and this is how you generate a list or one-dimensional array, and you're gonna get corresponding values. So this is another way of retrieving values of an array, and because we can save it into another variable, this is also a way of generating arrays modified in a different way. So, so that's how to retrieve and resort and reorder lists of arrays. And we can also generate random numbers. And here are a couple of examples. Okay, comment this thing out. And I'll comment, there's nothing here. Yeah, okay. So I can uncomment here this one thing. Okay, and let's see what do we get here. Control Enter. Well, and we check what's in U42. Well, we've got an array. It's gonna have 4 columns. Oh, it's gonna have 4 rows with 2 columns each, and it's gonna be filled up with the random numbers from a 0 to 1 range distributed uniformly. So it's same probability of values in any interval between 0 and 1. If you want to generate just a square matrix with certain dimension, you can use one argument. And then if we run this thing and check what's in the U44, now we've got 4 by 4 matrix with the filled in with the random numbers. If instead of uniform distribution, you want to have a normal distribution, instead of rand, you use rand n and then you're going to generate numbers that are coming from normal distribution. Those are things that are useful for generating synthetic data for different types of statistical calculations or testing scripts that are supposed to do something with your data, and you want to have data that you know how it know the property of and use it as a test input. So this is one way of generating test data. Use the random function to generate numbers that you need. Okay. So that's to finish up the random numbers and then operations and matrices. Okay, so now once we've got numbers, we want to do something with it with the scalar values, with the variables holding just a single number. It's just the regular math. There are functions, the math functions that are commonly used in math, and you recognize those things. With variables that store matrices, you're gaining access to all the operations on matrices as defined in a math, in linear algebra. Just matrix algebra is embedded in MATLAB, so you can do things right here. You can, for example, we've got here, you can multiply two matrices. Okay, we can do it by hand actually. So we can multiply a matrix composed of two rows. One is one, another one is a single column with two. You can multiply it by a matrix that now's got 1 and 2 as columns. Okay, and this is fine. That's right. This is a regular multiplication of matrices. You do have to be careful, and you've got to follow the rules of matrix multiplication. So you've got to have the appropriate number of rows and columns, otherwise the operation is gonna fail. So if, for example, we try to do the same thing, but we've got a mismatch in a number of columns and rows that are required, then it might work one way, because we've got, this is gonna work fine. If we reverse this thing, it's also gonna work. That's right, because this is also fine. This is another operation that's allowed. You're gonna get a different number. Oh no, this is not fine, right? Because this is, here we're trying to multiply on the left side a matrix with 3 columns, right? And we're trying to multiply it by a matrix with 2 rows. And this is not going to work. This is not how multiplication of matrices is defined in a math textbook. So this is fail. This is failing. This is very common when your data that's coming in doesn't conform to whatever the code expects. You might see errors like this. This typically means that there's a mismatch between whatever the code is expecting in terms of number of data points or number of experiments, and this is the root reason that sometimes somewhere inside the code your matrix multiplications fail. So, but if you follow the rules, if dimensions of the matrices are fine, then you should be okay. So this is okay. This is because one semicolon 2. One semicolon 2, because this is a matrix with 2 rows. 1, 2, 3 is a matrix with three columns, so we can, well, we can simplify this thing. We can make this thing into, let's say, A. Let's put this thing into B. Okay, this is gonna stay here. So now A times B is bad because, but B times A is fine. We can multiply, once more, we can multiply columns. If dimensions, we're running the sums is the same. So that's the bottom line. Apart from matrix multiplication as defined as defined in the matrix algebra, we can do dot products of matrices. Okay, so we can multiply, let's say, well, we can multiply two matrices as we've got here. Control C, Control E. This is gonna return a single number. That's right. This is dot product of two vectors. So this is 1 times 3 plus 2 times 4. That's 11. That's right. For dot products, the matrices got to be identical, otherwise they have same dimensions, otherwise you're gonna see the error. So some things won't work. So if we try to do a dot product between here, if we try to make a dot product between a column vector and this shouldn't work. Oh, it does work. Weird. If there's not, if there's, well, so you need the, I think dot product is, you need to have the same dimensions for dot product. So once more, that's how the products are defined. Okay, and then apart from matrix multiplication and then dot products, you can transpose matrices. This is another common math operation to make transpose. You specify, let's say, to have a demo. Let's try and make a matrix 1, 2, semicolon 3 and 4. So this is gonna be, let's see, sign it. Okay, so this is our G. This is our starting matrix. If we want to transpose it, you just say prime, and it's gonna flip the matrix around diagonal. Okay, if you use prime, this is technically a complex. This is transpose. This is complex transpose, which means if those numbers are complex, the sign of the imaginary part would be changed. So this is how transpose is done in the domain of imaginary numbers. If you want to do transpose without modifying the sign, you actually use G dot prime, and for real numbers it makes no difference. But if our matrix is composed of, let's say, let's make it IG, let's make our matrix composed of I1 and let's say minus I and 2. Okay, so this is our IG matrix. So now we've got 4 numbers, but they are they are complex, right? We've got, this is just I. This is imaginary part, no complex, and real part is 0. Here we've got different combination of real imaginary parts, and same with the other 2 rows. If we perform IG and transpose on that, you see that the signs are changed. Yeah, there we've got 0 minus I coming out from this value. So we change sign on complex side. Same thing here. The sign got changed. Okay, but this element ended up here. So here's the sign change here. If we don't want to have the signs changed, we use IG dot prime, and now the signs are not being changed. So those are common ways of manipulating matrices, changing the flipping orders, rows with columns or vice versa. And you can either do it with retaining the sign or changing the sign of the complex numbers in case the values are real. If are complex, if they are real numbers, then it doesn't matter. Either way is going to return the same value. Okay. Apart from and so far those are operations that are defined in linear algebra. This is how you multiply matrices with vectors and whatever. This is pure math. In some cases, you want to perform operations on a element by element basis. So let's say you've got 2 matrices. Let's say you've got one that's something like, okay, let's make it let's make it something called, let's say I2, and I'm gonna make it by multiplying by 2 identity matrix that's sized 3. Okay, so my II2 looks like this. Okay, and then I'm gonna make another matrix. Let's say make it 4. Okay, and let's make it 4 times IY. Let's make it 3. Okay. So if we multiply those 2 things in a conventional way, let's see, what do we get? We've got normal multiplication rules. If we multiply, okay, and let's make it something else. Okay, so let's make a more complicated thing. Let's try and let's add 1 to it. Okay, 1, 1, 4. Okay, so here on. Okay, let's make it. Okay, let's try it this way. Okay, so here we've got something that looks like this, and if we multiply it by let's try I2 times I4. Okay, so doing this way versus if we do it this way. Yeah, here we go. Okay, so to have it better. Okay, so here's our one matrix. This is just identity matrix with the multiplied by 2, right? The other one here it looks like this. If we multiply those two matrices in a conventional way, this is the result. Right? You do regular matrix multiplication of 3 by 3 matrices. If on the other hand you want to multiply this value by this value and this value by this value, this value by this value, so you want to do multiplication on an element by element basis, then instead of saying you multiply by star using star, you say dot star. Okay, and then if you do this thing, the result is different, right? You're, instead of getting a formal multiplication of matrices, which results in non-zero elements away from diagonal, multiplication by the matrix we had by I2 by a matrix with 0 elements, zeros things that are off diagonal. So this is in case you want to perform operations on an element by element basis. The convention used by MATLAB is you use dot followed by operation. So you can multiply two things together on element by element basis by specifying dot star II4. Okay, and this is multiplication of two matrices. Technically, let's see, you can raise a square matrix to power. That's right. You can have AI2 to power of 2, so you multiply it by itself. That's right. Same thing with II4. This is the same thing. You can multiply. You can square the matrix here. But if you want to raise each, and this corresponds to multiplying II4 matrix times II4. To convince yourself, you can always do II4 times II4. That's right. This is the same. This is equivalent to operation here. If you want to actually raise each element of an array to a certain power, you can, instead of doing II4 caret 2, this is what we had before. If you specify dot 4, then the result is different. Then you take each element in a matrix and raise it to a power. So this is different operation. This is performing raising to power on a element by element basis. If you use just caret, then you're multiplying two matrices, the same matrix twice or whatever number of times. So this is according to matrix algebra. So there's another operation that can be performed on a element by element basis. Okay, and few other functions. You can get the smallest value either within each column of an array or within each row of an array, or altogether by using the min function. Okay, if we want to find what's the mean smallest value for each, well, we'll see for each Let's try. This is good. Now this is symmetric, damn it. So let's make a simple array. Let's try what's in any. Okay. Let's do. Okay, let's make it from a scratch. 1, 2, 3. Let's make 1, 2, 3, 4. Okay, so here we've got a nice thing. Okay, so now if we do min a, we are getting smallest value in the first column and then smallest value in the second column. So it means that min a is returning the smallest value on a column-wise, in a column-wise manner. Okay. If you want to do it in a row-wise fashion, you've got to specify which dimension is supposed to be used for scanning. So if we want to scan the rows to get the smallest values, then we specify as a second, where is it? As a second argument here, 1. This is the first dimension, which is always rows. So if we do this thing, min a, what in the word? No. This a, no. Why is this? Here. No, it should be. What is A? This should be. Okay. And if we do min a, sure. Oh, do we have to do it? Well, if nothing works, we can always say min here, and then we can always go to help. Okay, and then in help, we're gonna see how to get the values you want. Okay, so here, if a, here's our case. Okay, so if, as I did it before, we specified the mean of a matrix with two-dimensional matrix, then I did minimum value for each column. Okay. Okay, I do have to provide the dummy argument here. Okay, so it means I've got to get two columns. I've got to specify this thing as here. Okay, and then yeah. So okay, so A is here, and so now here our matrix A is 1, 2, 3, 4. To get the minimum value in each row, we've got to specify, call the function like this. There's, for some strange reason, a dummy argument to be used, but this is second dimension. If we want to do it along the first dimension, we do it, I think, this way. And now our starting A. This is our starting A, and here we've got we had the minimum for a column and for the column. So this is how to get mean values in each column. This is how to get mean values in each row. There's some extra argument which would is to be specified to get the right number. The shortcut for whatever you've got here is just this. This is default. This is column-wise averages. Same thing holds for maximum values and for averages. So that's another set of useful functions. Okay. In case when everything else fails, you can perform operations on and prepare your data in a matrix or process data in your matrix by hand. What I mean is you can explicitly go, I mean, you've probably noticed that every operation on a matrix involves going over each row, going over each column and performing in a repetitive way some sort of operation. Element by element. So there's a lot of repetitive computations involved. You can, and you don't see this thing, this is embedded in the rules of matrix algebra and how the operations that you're using are defined. You don't do those things by hand. This makes it fun if you're dealing with any sort of linear algebra, because you don't have to do those mundane operations. If you do it on a piece of paper, MATLAB is gonna do all of those things for you, so it's convenient. But sometimes you've got to do those things by hand because you can't find the pre-made operations that you want to do. To perform those operations, you use so-called the for loops. The way it works in general is that you specify a snippet of code that looks in general like this. You start with saying that for variable taking certain set of values, and here you specify in one way or another a list of values, okay? Here is the simplest case. I just want to have I take value 1 and then 2 and then 3, okay? And then I want to just show them. So I'm just gonna display those values on the screen. When I run this snippet of code, all I see is I'm gonna see the values 1. Well, here let's clean the command window, clear it here, and then if I run this snippet of code, I'm getting the 3 values displayed. Okay, so this is sort of stupid, but obviously whatever goes here can be a piece of code that does something. Okay, we can, for example, instead of displaying we can multiply I by itself. Okay, and well, let's display it for this. Let's display it. So okay, here we go. So just show what is the square of each number if we run this script. So now we've got a series of squares. So this is a general way of repeating operation over and over and over again, and each time you execute operations between the for and n line, whatever is here is gonna be run with the value of I inside the block, taking the values from the list. Okay, so we can specify a list as here explicitly. This is a list of or list of 3 numbers. We can specify it as a range, so we can say we want to go from 1 to 10. That's right. This is another option of specifying a range of numbers. That's right. This is perfectly valid. Okay, and we run this thing now. We're gonna get squares and so forth. Okay. Now, the problem here is that if you use explicitly loops, this is very, very slow. This is done by MATLAB in a way orders of magnitude slower than if you use equivalent built-in operation. So you should try as much as possible to avoid this thing. Just to demonstrate it to you, let's try to do something a little bit more complicated. Okay, so let's try to start with, okay, here let's try to start, let's try to start with a number of times you want to repeat an operation. Let's say this is 10 to 6, so this is 1 million of times. So I'm gonna set n to 1 million, that's right. I'm gonna set up a variable when I'm gonna start adding things, okay, and I'm initializing it to 0. So before everything starts, sum is gonna be set to 0. And now here's my block. Here's my block starting with 4i going from 1 to n. So it means I'm gonna change the value of i from 1 up to 1 million. Okay. And then I'm just gonna add up a random number from a range of 0 to 1 drawn each time I'm passing through the loop, squared. Okay, this is something very, very simple. This is just adding up squares of 1 million random numbers going in, starting from the 0 to 1 range. Okay, and then I'm going to display what the value is. Okay, so let's run this thing. Okay, and see what happens. Well, we're getting whatever number here. If we don't square, or if we just raise it to power of 1, and if we run it once more, we should see 0.5. That's right. This is each random number here is drawn from uniform distribution from 0 to 1. So on average, it's gonna be 0.5. If we draw it 1 million of times and see what's the average value of those 1 million of random numbers, it should be somewhere close to 0.5. So this is returning us what we expect. If we though raise each random number to the second power, if we square it, those numbers are on each of those numbers is less than 1. Square root of a number that's smaller than 1, it's less than itself. So the sum of those 1 million numbers should be less than 0.5. So we're getting 0.30. So this makes sense, roughly, right? So this is done by hand. It can be done in one line by specifying that we want to generate random numbers. We want to generate, let's see, what's the syntax? If we do it this way, we've generated 10 random numbers. Okay, we've got to specify one, because if we just generate around 10, we're gonna actually around 10. Let's make it smaller, around 5. If we generate, if we say, as I did before, where are we here? If I say round 5, this is gonna generate 5 by 5 matrix grouping with random numbers. If I want to have just one-dimensional array, okay, I've got to specify I want either a column vector. If I say that I'm gonna fill our array along the first dimension, or if I want to have columns, I say 5, 2, and then 5, no, 5, 2. Well, sorry. So this is number of things along the first dimension. This is number of values along the second dimension. So this is 5 by 2 matrix. This is 5, 1. This is 5 rows, 1 column. This is one row, 5 columns. Okay, here we go. So now, if we want 1 million of those, we would say here 1 million. Okay, n is set to 1 million. That's right. So this is gonna be 1 million of numbers. Now we want to raise each of them to a second power. That's right. So we can just do dot caret 2. This is gonna do the raise each element of our list to the second power. So it's gonna square each element of this is a matrix with 1 million of elements, right? So this is equivalent of doing this thing 1 million of times at once. And then if we want to get the average of this thing, we can just say that we want mean of whatever is here. And if we want to do it on a column-wise way, because we've got one row with many columns, we've got to do this funny thing with a dummy argument and 2, because we want to get the mean over columns. So I think this one should get us what we need. No, oh no, we don't have. We've got for mean, we've got only this. Yeah, and then if we assign it to something, oh, let's say if we assign it to something. So here's our mean calculated in one line. So this is equivalent of what we did higher up here. That's right. We generated n 1 million of random numbers. We then squared each of them one at a time. So this is corresponding of multiplying each element of array with itself. That's right. This is not matrix multiplication. This is multiplying the first element by itself, second, and so forth. That's right. This is what we've got here. And then we are calculating a mean value of all the elements in this list of numbers, right? This is exactly what we're doing here, but in one line. One issue is laziness, that's right. One issue is that we're typing less to do the same amount of work. So this is why to use this thing. But there's another reason. But to show you why it's better to find the short ways of doing things, the more concise ways of doing things will have to actually run this piece of code as a standalone script. To do this thing, I'm gonna in editor add another file. Okay, so here's my empty file. I'm gonna take this piece of script and I'm gonna just copy and paste it here. Okay, so here we've got a very, very simple script that's doing some sort of math. Okay, and we can run it. Okay, we don't have sections now. We've got just entire scripts to be run, so we can say we want to run it. And it's gonna ask you, MATLAB is gonna ask you how to name it. At this moment, it's a new file with no title, so I'm gonna call it, let's say, mean test 1. Okay, and I'll save it. Now we've got the script with the proper name, and then we can run it. Okay, and we're getting a number. If you rerun it, you see we're changing the value returned each time is slightly different. Yes, it's fine. We're generating each time, we're generating another set of 1 million of random numbers. So each time the mean value is going to be slightly different, but it should be somewhere close to whatever is expected. Okay, how long does it take to run this thing? Well, we can try to clock it with your watch. Either way is to use a profiler here. Okay, it works only on a script saved in a file, so that's why I saved the snippet I had into separate file. And then if we run a profiler, it's gonna, if I'm lucky, pop up its own window here. I'm gonna take a moment. Okay, and now I've got an option to run different things. Well, at this moment, I've got only my mean test 1 script to run. I can run it. Okay, and it tells me it takes about 0.8 seconds to run. Okay, is it a lot or is it fast? Well, we've got something to compare it to. That's right. We've got our concise version that I had here. That's right. This is my equivalent version of doing things. So let's make another file. Okay, and let's put this short version, Control-C. Let's put it into the other file. Okay, I'm missing the N. So let's set N here to be 1 to 10 to 6. This is the same. Okay, so here's my short version of the same operation. That's right. I'm gonna save it this time explicitly. Okay, save as. And instead of mean test 1, I'm gonna call it, let's say, mean test 2 and save it. So here's my script that does operation like this, which is equivalent to whatever we've got here in explicit way, right? So now we've already tested how long this script takes to run. We can do same thing for our concise version of a script. Okay, let's try to run it. So we go back to provider. Okay, now we pick, no, I should be able to find, no, go away. Okay, so let's see first if this thing runs. Yeah, it runs. Clear, maybe not here, clear the command line, and let's see, does it run? Something's wrong. Something wrong. Let's see. Something's wrong. Let's see. Okay, let's try n equals. Now let's round off from 1 to n squared and it's here. And let's, yeah, what if we make, let's, okay, so let's make n 6. Let's do, okay. Here's our n, and now let's see what's happening here. Yeah, okay, so this should be fine. So here's what we've got here. Okay, this is my number. Right. So, okay, let's do display. Yes, okay, let's try it this way so that it spits out something. Let's run it here. Okay, run it here. Yeah, okay, it's getting us a number. Okay, so back to provider. Okay. Now, okay, so now, okay, so it's, I know it might be issues with the laptop. Okay, so now we've got the other script to run. Let's try to run it. Okay, and here's the difference. Okay, the short version of the script, it's not only that this thing is shorter, it's also running about 10-20 times faster. That's right. Here, the test2 ran in 3 milliseconds or 4 milliseconds. If we try to run equivalent version of calculation done with explicit loops and we run it, here's 0.7. That's right. This is significant. It might be short because this is a simple computation, but if you've got something which takes in optimal version, let's say 5 minutes to calculate, but you write it in a suboptimal way, which is running 20 times longer, then instead of 5 minutes, you've got several hours to wait. That's right. So that's the point, that it's not only that you save time typing less, but then here the version that's using built-in operations is much faster than the version which you put together with the for loops in any way where you explicitly iterating over things. So in many cases the explicit loops are useful and they do have their applications, but if you're doing numerical calculations, better to find out and spend time thinking how to do it using the built-in operations instead of putting things together by hand. It's gonna be way faster. So that's something to be aware of, and that's why you should try to optimize how you write your code so that you perform operations using built-in functions instead of things put together. Where does for loops have use? Well, if you look at the typical workflow, a typical situation where you perform your computations, you typically read your data in from some sort of a file. Those might be experimental results. This might be something that someone gave you, something that you got off the network, whatever. You're gonna read your data in. Then you're gonna do some number crunching. You're gonna do something with your data, and then at the end you're gonna spit the data out into another file so that it stays that you can put it into your paper, publish, whatever. Okay. Whatever is happening when you're reading data in and whatever happens when you're writing data out is relatively slow, because writing to drives getting stuff off the network is typically slow. So if you add extra overhead by using those explicit loops, it's not gonna hurt you much. You're gonna lose a little bit of time, but it's gonna be very small, very low cost compared to how much it takes to actually read the data of the network or read the data of the driver right there. So at the very beginning, at the very end of your programs, you might see those for loops or whatever loops done explicitly, because it might be easier to get the data, format them in a way that your script is gonna take them in. So this is where things done in the explicit loops do have do show up. Typically this would be seen when you're gonna try to save your data into a file and then retrieve it. Let's try. Okay, so let's say we've got some sort of computation that we want to generate some whatever pieces of data, and then we want to save it to a file so that we don't have to regenerate it over and over and over again. We want to have a file with the data in. Okay, we've got to specify initially a name of a file that you want to save the data to. That's sort of reasonable. That's right. You want to know where to put stuff in. Okay. Once we've got the name, let's say this is gonna be our file. Okay. We first got to open the file. Okay. And to do this thing, we use a function called fopen. We pass as an argument the name of the file. This is our test data, whatever. And we've got to specify if we want to open this file for writing or for reading. That's right. You can either read from a file or write to a file. So if we want to write, we specify W as a string. This is a string, so you've got to put it in single and double quotes. This is opening this file, anticipating that we're gonna write data there. Okay, and this is returning as a variable, which a value that we assign to f out or whatever variable. This is something that's later on used to refer to this file. If we want to write to this file, we're gonna use this variable as something, as a parameter to a write function, okay, or whatever function used to write. Okay, so far we do have our file open. Okay, so now let's do in this case in a sloppy way. Let's do a couple of for loops. Okay, and what we're gonna do is comment this thing here, and comment this thing here, and comment this thing here. Okay, what's happening here? Okay. well, I've got to generate my data here, which I think is coming from somewhere before. Okay, so here, okay, let's uncomment everything here. So I've got to generate some sort of data to have. Okay, and this is in the for in the sloppy. Here. Here. And here. Okay. What do we have here? Okay, what do we have here? Okay, so I've got, let's say, 1,000 rows. This is the count of rows stored in one variable. Here's a count of columns stored in another variable. Okay, and I'm just putting in this variable numbers from 1 up to n calls. So this is gonna be 1 up to 10, but I'm gonna square each of them. This is as before. I take 1 and square it, and then take 2 and square it. So this is gonna end up in my STD. Okay. Now I do have in my data, initially I've got the 0 stored with 1,000 rows and 10 columns. Okay, so this is gonna be a matrix with filled in with zeros, and it's gonna be with 1,000 rows, 10 columns. Okay, and then what I do here is I go over columns. Okay, and then I'm storing random numbers. Okay, this is gonna generate n rows. It's gonna generate 1,000 values that are random. It's gonna multiply it by what's in here, and in here in my STD, I do have a 1 squared, 2 squared, 3 squared, and so forth. So I'm gonna have a random number in a range from 0 to 1 multiplied by something coming from the other matrix, and then this is going to go into columns of my data. Okay, if we want to see, yeah, okay, so this is where it goes. Okay, and then I'm just printing it to see what's there. Okay, so that we'll see what's going on. I can change the number of rows to, let's say, 10, and let's make just 3 columns so we don't see too much stuff printed out. And let's run it. Control Enter. And it must be positive or logical word. Fprintf. Let's see. Okay, let's comment this thing out first and see what happens. Oh, nothing. Well, if nothing happens, then it means it's run. Well, let's clean it. Okay, let's run this snippet. Oh. Run this snippet. Okay, and then let's see my data. Let's see, what do we have? Okay. Okay. We're getting for this piece of code, 10 rows, that's right, 3 columns, and then in each column, we're getting the values, okay, drawn from a random distribution and essentially a bunch of numbers. Okay, I'll clarify what this thing is tomorrow, but we just have a bunch of numbers we want to store somewhere in the file. Let's make it more. Let's get our 1,000 things, and let's get us 10 columns. Okay, and we're okay. If we check what's there, okay, we run it with 10 and 3 as parameters. So if we want to check what's in my data, we can do size my data. Okay, oh, there's a typo. Size my data. Okay. Yes, I did. And we do have in my data an array with 10 rows and 3 columns. If I rerun this code with 1010, I can rerun it. And then if I check what's the size, now we've got 1,000 rows and 10 columns sitting in my data. Okay. So this is what we've got sitting here. There's somewhere here a typo that's the reason this thing doesn't work. So we'll get to printing stuff tomorrow, okay? But if we want to save it to a file, what we do is we go over the rows of our matrix, okay? And how many is there? This is how to get the number of rows of the data. The size is here, returning number of rows and number of columns. This is a list, right? This is a list with first value being 1,000, second 10. So if we want to just get the first value, you specify that we want the first value, which is corresponding to number of rows. For each row, JJ is gonna be set to 1, 2, 3, up to 1,000. This is going up to 1,000th row. For each row, we want to go over columns. This is gonna be our index position in a column, and we vary it from 1 to the size along the total number of columns, which is this number, and we can retrieve it by using size my data, but with 2 to specify that we want the second position or number of columns here, okay? And then once we know what's the position along rows and what's the position along columns, we're gonna get the value. That's right. My data JJKK is a JJth column and KKth JJ's row and KK's column. Okay, so this is what we want to, this is what you want to write to a file, and the function to use is fprintf. Okay, this is a function which takes as a first argument our file, whatever fopen returned. Okay, so this is our file that we opened here. And then we specify so-called format string. This is specifying how the number should be converted to characters that go into a string. into the file. Okay, we can try how this thing works just in the console. If we skip the F out, if we skip the file that we want to write, we're gonna write to the console. So we can do F print F. We're gonna skip the file handle. We're gonna skip it, and we're gonna specify only the format string, which looks mysterious. It's %63F, and then I'm gonna add here \n, and then I'm gonna say my data, and I know that I can print one of this thing, let's say position 2, and let's see what happens. Okay, how to demystify this thing? Okay, this is easy. This is second, the value in my data table, second row, second column. This is easy. What the heck is this? Okay, well, we're specifying every time we want to print a value, we use a %, and then what follows is how the value is supposed to look like. In our case, we want to print a floating point number, so we use here F. This means that the value is supposed to be printed as a number with the decimal points. Okay, we want to use 6 characters to print entire number, and we want to have 3 decimal digits after the period, right? So, and then once we print this number, we want to go to the next line. So \n is print a new line. So it's gonna move us to the next line. Okay, and this is what we've got here. We've got 1 character here in front of it. And total is empty space 3.299. So there are 6 characters that we split out. We've got 3 decimal numbers, and total is 6. So this is exactly what we've got here. If we want to make it, let's say 8, or if we want to make the printout wider, let's say if we want to make 10 character wide printout, then we can specify total width of that's used for printing the value as 10. If we want only 2 decimal points instead of 3, we can say 2, and now we've got only 2 decimal points. So this is the way to format real numbers with decimal floating point numbers. If we want to print 2 numbers in a series, let's say we want to print out 2, 2 and 2, 3, we can specify this thing as saying my data. Oh, where are we? No, wrong place. We can specify this thing as my data, another argument, my data. Let's make it 2, 3. Okay, right. But now we need another %sign and another specification how to print out the next one. Okay, so we can put a few spaces here, and we can say, let's say %10, and then 2, and then F, and new line stays here. So now when I run this piece of code, I should see 2 numbers. Whatever is outside of the blocks between the % and F is printed verbatim. So if we want to say something here, let's say let's say, if you want to say, put something here, val1, okay, this is gonna be printed explicitly in front of our number. Then there's a few empty spaces. Well, if we want to put something else, we can put, let's say, two columns, okay, and then we can print another number. So now what we will get is a line that looks like this. Instead of spaces we want to use commas, we can put a comma here. That's right, we can just put a comma here, and then when we print it, we do have a comma as a separator. If we want to put a tab, okay, we can put \t, which stands for a tab. This way you're gonna generate a tab separated file with the value separated by tabs. This thing is converted to a tab when printed to a file or to a screen. So here's another version. So if the number is integer, if it's just 1, 2, 3 without decimal points, instead of using the %f format, you can just say you want to print out 8 characters with the decimal number there. So this is another version of a format where you specify that it's going to be a decimal number, or you can just skip the width, just say %d, and then the width of the printout is going to vary depending on how large the number is. So the same thing is going to happen here if you say, let's say, I think say this thing should be valid. If you say it this way, and let's say here we print out 2, let's see what happens now. I'm missing this is my data too. Oh, because I made a mistake. I got here a bracket for no apparent reason. Let's try it now. Let's try it now around here. Yeah, so now I'm printing 2 and then tab and then floating point number without any sort of padding. If I want to get rid of the leading stuff here, I can remove things here. Okay, and if I run it, I've got this 2 printed as a decimal, as a integer with no padding whatsoever. Then there's a tab, whatever the tab is showing up as, and then I've got the floating point number with no padding, but with 2 decimal points. So this is the way to see if the format of what you want to write to a file looks fine. You can play with some numbers that you came up with, and then try printing it. Here we've got the version that's going to be used to write to a file. So our file handle goes back. Okay. That's going on here. I messed up things. Okay. Then I'm printing a floating point number with 6 characters reserved for it, 3 decimal positions. Then there's a space. Okay. And I'm getting data from the jth column case and jth row case column. Okay. And I do this thing for every column. So there's gonna be, if I had 10 columns, there are gonna be 10 numbers in a row. Okay. Once I'm done with printing out one row, I've got to print out a new line, because otherwise it would continue in one long line. Okay. So this is gonna generate me a one row of data by printing values in each column for a given row one at a time, and then adding a new space, new line at the end. And I'm gonna go over all the rows. So this is going to print out line by line our data into a file. Okay. And then once we're done with writing this thing out, we've got to close the file to send stuff to the drive. And then if we run this thing, okay, the script did run, didn't spit out any errors. And we do have now a file here called test data. Okay, and if we open it, if nothing bad happens, well, it's a slow thing. Okay, things are happening. Hopefully. This is a large file. Yeah, here's our file. That's right. We've got 10 columns. We've got 1,000 numbers with the 1,000 rows with the numbers that we wrote to a file. Okay, we can open this thing if one prefers. We can open it as text. It's gonna be faster. Here's how the file looks like. That's right. We've got 10 columns separated by spaces. And here's our file. How to get it back into our program? Well, it's easier than writing. All you've got to do is you've got to specify that you want to import data in your file. Okay, and if we run this snippet of code, okay, this is test data 1, test data 1, okay, and I'll clean all this mess here. I'm gonna do clear workspace. Okay, so then this is the file that was just created. Okay, we will run it, and here's our data that we wrote into a file. So assuming the numbers in this file came from calculation that took 100 minutes to generate, we can save it, and then next time we want to continue on and process it more, we can retrieve it from a file. That's right. So this is how you save data and then retrieve it. Writing is sort of messy because you've got to think about to format it, but reading it once the format is reasonable, it's relatively simple. This is just a single line. And in many cases, data generated by other programs. Data generated by other programs in other formats can be read by MATLAB in one line. You'll have to see what's there and do things in the right way, but the reading files should be relatively easy. Okay, that's all for today. I'm gonna stop. I'm gonna turn off the recordings. We'll continue on tomorrow with doing more things. Let's stop recording. Yeah.